Can you hear me okay? It's very weird to chair the session and then speak in the same session. I was notified I need to do chair this session just a couple of days ago. And then thank you so much for staying here. And also sorry for the delay. We start too late and 15-minute delay right now. I'll try to finish up my talk very quickly. Before I start, how many of you do bio research? Oh, there are two. Okay, this is three. Thank you. How many of you are interested in bio research? It's better. Okay, thank you. Probably this is the lowest number I ever given my talk. To introduce myself a little bit more, I'm currently the J. Craig Venter Institute. As I mentioned earlier, if you don't know, it doesn't matter. I'll show you the institute in a minute. I'm professor there. I used to be the professor at Washington University in St. Louis, in the middle of nowhere. I just moved, 3 months ago. I constantly traveling. This year I counted total days of traveling would be 190 days. And then as I mentioned, this is gonna be my talking to the lowest number of people interested in bio. Let me try very high level presentation instead of giving details, given your low interest in bio. So before I start, I need to claim, this is my great disclaimer about my conflict of interest. I start a company called Moonshot Bio. Why not? My last name is Moon. I want to do something crazy. And then I start a company called Moonshot Bio. I believe many of you already know the most famous engineer in history, Bob Langer, and of course the MIT professor. He started a program basically giving you the money up to $100,000. This changed my life. What I meant, I basically now start a company based on this money. But I'm not talking about this money. I'm talking about my status at home. So my more than 20 years of marriage, my wife always tell me, "Oh, honey, shut up. I don't have any interest in your research. Just let's have good dinner." Whenever I'm talking about my research, it doesn't matter how much money I'm getting, the grant. It doesn't matter whatever publication in Nature journal, whatever. It doesn't matter. She just want to have some money to home, right? And then one day I got this money. This money not going to my research account. This money came to my personal account. I'm talking on my bank account. And then suddenly my wife asking, "Oh my God, what are you doing? What kind of research are you doing?" And then suddenly my status used to be over here. And now over here, still my wife here, my daughter is up there. So that's very important for me, not about the $100,000. That basically changed my life, my marriage status and everything, my respect level from my family members. So this is very important. So I thank him a lot. So that's one thing I want to tell you. So I have the project, more than 10 projects funded by the government. I'm not going to talk about this one, but I'm focused on the project, that is about the company related. And then this is actually the institution I'm talking about. This is the Craig Venter Institute. And to give some idea who Craig Venter is the person who did the human genome sequencing for the first time, beating all the nations when at the time all the people competing each other, including NIH. And then he used to be NIH. He came out of the NIH because the process or procedure they tried to do is so outdated, and he studied new method, completely revolutionized the biology field, and then did the human sequencing for the first time, beating all the team. And then, but it doesn't matter, right? Because you are not interested in biology. The most important thing is this is my institute overlooking Pacific Ocean. And then MIT, much better institute, I believe, but there is no ocean you can overlook, right? So that's my point. So if you are postdoc candidate interested in joining bio research, suddenly you change your mind, just send me email. My email is, of course, the tsmoon7@gmail.com. So let me start with the serious talk. So even if you are not interested in the biology, you're probably interested in the global problem, including the climate crisis, energy problem, also pollution, etc. I'm very passionate about this problem, especially the global problem related to the climate. And I hate this guy because this is a waste, especially the plastic waste. That's a huge problem in the world. But this is actually saved my life because I talked about earlier my trip, more than 190 days a year. And without this one, I cannot survive. So I always have this one, empty bottle, fill up this bottle with the new water anywhere in the fountain. This is not actually recycled all the time. I cannot travel. But still the problem is too many bottles in the world every single day produced. And what I want to do is rather than using other methods, there are multiple different methods to tackle this problem, but I want to use a biological method using, I call it magic bacteria that kind of uptake whatever waste, including plastic or CO2, and also the plant-based agricultural waste into some high-value chemicals. Today, we doing all kind of different research, including CO2 reduction, also the biomass, including the agricultural waste or plant waste. But today I focus on the plastic waste because that is I start the company based on this technology. So before I going forward, I just want to give some crazy idea. I'm thinking about that more than 10 years, but I couldn't put it in the written form because at that time I was just assistant professor 12 years ago. I don't want to make all the big guy pissed off because I'm talking about some crazy idea. If you are not interested in bio, but if you heard about metabolic engineering, I will give you a definition of metabolic engineering for the last 30 years. Metabolic engineering is basically the technology or field. Basically, you take whatever biomass, typically the glucose, but the glucose is problematic because that's based on the food. And then using that feedstock, glucose, and then use one microbe, typically some whatever microbe, and then typically we used to use the yeast or E. coli, very traditional one, and then convert that into the whatever compound, but one product using one bioreactor. So as you can imagine now, I'm talking about one feedstock, one microbe, one bioreactor, one product generation. But why we kind of stick with this one situation rather than talking about a bit broader or bigger picture? So after I got tenure and then after carefully waiting for my right moment, I would say a little bit bravely put this idea out. And then now I see something completely different idea. Instead of thinking about one feedstock, I'm now talking about entire ecosystem. And then in ecosystem, there are multiple feedstock, including, of course, CO2, also waste, including the plastic waste, etc. And then multiple microbes in that ecosystem. And to give some idea, photosynthetic bacteria could capture CO2 and then potentially reduce greenhouse gases and then convert that into even high value chemicals in the soil or in the water, or even you can say, entire planet. So now I see the entire planet as a huge bioreactor. In that bioreactor, as I mentioned, photosynthetic bacteria could potentially reduce greenhouse gases. And then in that, soil environment or water environment, there are interesting bacteria called nitrogen fixing bacteria that potentially fix, highly efficiently fix nitrogen that into ammonium. That's the biggest problem in the world because we, as a developed country, use too much nitrogen fertilizer, and then that lead to sometimes nitrogen fertilizer problem, including algae bloom, etc., that destroy ecosystem. But in the meantime, some company, some people or country like the Africa or some Asian country, they don't have enough nitrogen fertilizer. Because of that, basically their crop yield is very, very low, only 20% or 10% of what we're getting. So if you have this kind of nitrogen fixing bacteria somehow deployed into the field, actually that is also commercialized by my classmate or the lab mate. They actually start a company called Pivot Bio. And then if you have that technology, you can deploy that bacteria into the field and then increase the nitrogen fixing ability. And then as I mentioned today, my topic is plastic upcycling. If you identify or develop or engineer microbe that potentially eat plastic waste and then convert that into high value chemical, now you're talking about plastic problem solution by using microbe. This is my basically vision, and then I'm talking about huge bioreactor, and that is actually planned as a bioreactor. So this is a crazy idea, I know, but we kind of recently start the project. So to make that happen, we need to have some tools. And then first I want to introduce to you, especially for people interested in biology. Before, when we study biology or study one single microbe, what we done is we basically delete one gene at a time and then understand the function of that gene. That's how we understand all the genes we have. If you're not that much into the drinking alcohol, probably you don't have alcohol dehydrogenase. That is a key enzyme for the break down the alcohol in the beer or wine. And then the way we know is we basically delete that gene and then see you don't have any metabolism of alcohol. That's pretty much what we've done. But that's a single cell level or single strain or single entity level. But can we do the same thing in the entire microbiota or entire microbial community level? Now we have the tool using so-called the CRISPR system. And then basically the CRISPR system, basically you can use that as targeted killer. That means entire soil system or water system. Now you have the method or approach or tool. You can target only one bacterium in the community and then kill only one bacterium. And then you see the function of that bacterium in the society, in the community. That means if you wanted to kill only one pathogen in your gut, in the soil, you can target only that pathogen without using some chemical or antibiotics. In that way, you keep all the beneficial bacteria, including nitrogen-fixing bacteria, but only kill the bad guys in the community. And then at the same time, you can use the same tool, but now use one more step, basically integrate antibiotic-resistant gene into the specific target strain or the specific target organism, and then only that guy survive when you just treat with the antibiotics. In that way, you can easily isolate the bacterium you wanted to identify that potentially including nitrogen-fixing bacteria. So that is actually, we published recently and then we kind of expand the idea. And then now we're using that technology in real sample. I'm talking about real soil, real water, etc. So speaking about the plastic, I have probably only 7 minutes, I guess, to speed up. So basically this was my idea when I was traveling. And then that was my shoe. After 71 days of non-stop trip, I'm seriously talking about 71 days without coming home and traveling to give 25 seminar 2 years ago. And then I found many holes in my shoe. And I realized I probably want to recycle the plastic to make my shoe at the time, but this is my joke slide, nobody laughed, unfortunately. Anyway, so my project is basically about not the recycling, but I'm talking about upcycling. Upcycling means here is basically using waste and then making high value out of this waste. As you can see, I mean, this waste probably costs very little, but still costs some money. But we are talking about now is not only polyethylene terephthalate, there's a PET over here, but now we have the technology, we can now convert mixture of the PET, polyethylene, polypropylene, polystyrene. I'm talking about mixture. And then the most important key technology that actually triggered me to start a company is it doesn't matter regardless of the composition of your plastic waste. Now we have the technology, the chemical method convert that into smaller molecule, basically breaking down. And then I have the two magic bacteria converting in terms of data, 100% consumption at breakdown compound. But my lawyer said, don't say 100%, even though your data showed 100%, you should say almost 100% because that's a legally right term. So basically now, regardless of composition of original waste, we now have the technology that convert it into the high value chemical at the end of the process. And this is very important because my plastic waste is different from your plastic waste composition. Today's composition different from tomorrow, right? So because of that, now we have the solving the problem of feedstock, heterogeneous feedstock problem or inconsistent consistency. So because of time, I just move up very quickly. So I chose the one, chemical that's a carotenoid. It's kind of blocking that one. But main idea is there are one company doing very nice job, scale up and then making the PT out of PT waste. This is a French company basically using enzyme to break down the PT into the monomer, but this is not mixed plastic, only PT, only this guy, and then convert it into the monomer of the PT. There's a two monomer, TPA and EG, and then purify, and then repolymerize using chemical method to make the PT. This is a very important technology because this is a recycling, and then basically this is a huge market, as you can imagine. But the only problem I see here is the cost of this process. The cost basically is $2 per kilogram. I checked with the company employee. Based on my calculation, I'm talking about techno-economic analysis. This entire process should be at least $2 per kilogram. How you survive because the current PT price is only $1 per kilogram or less. And then the company employee said, don't say I said to you, yes, your calculation is right, but the way we survive is French government giving a lot of money to the company, of course. So based on that conversation, I see, this is a huge market, that's great, but it's not gonna work. Probably it should work. I want them to succeed, but not economically viable. So we chose the compound that's a minimum $100 per kilogram. And then the other important thing is the carotenoid, including beta-carotene or lycopene, is currently produced by extracting the compound from the food, including tomato and then carrot. So lycopene from, basically tomato. But as I mentioned earlier, a little bit about the economic inequality or agricultural inequality, food inequality I'm talking about. We waste too much food in this developed country, but a lot of developing country, many people die at this moment because they don't have enough food. I know that one because I have the student from Africa, and then he lost two brothers because of hunger. he doesn't have electricity at the time at home. And then now we're talking about converting food into the chemical because of high value. So I want to completely destroy this ecosystem by developing this compound using, of course, the plastic waste into the high value chemical, including light compute. So this is my concept, and then this is all the detail, you don't need to worry about because you are not the interest. So main idea is basically we now have the technology, as I mentioned earlier, plastic into high value chemical. Actually, that should be the red color, but somehow the picture is not delivering the right color. But the current titer is, used to be around the 1,000 microgram per liter. And then after multiple different metabolic engineering technology, we actually now have the around 20,000 microgram per liter. And this sounds a lot, but unfortunately not commercially viable yet. And then this should be at least the gram per liter scale to consider scale up. And then, but we start from the microgram per liter scale all the way to 20,000 microgram per liter. The 20,000 fold increase lasts a couple of years. And then I believe 3 more years, that will become the 1 gram per liter. If that happens, I sell my technology to the company, retire, and I have my mansion in California, and then drinking a cocktail, and then seeing sunset, and I'm done my career, I guess. Hopefully that happens, and that's why my wife is so excited. I'm talking about the California, right? So this is the boring data I mentioned earlier, 100% conversion, and I would probably skip all of that because of time, limit. So also another thing I want to talk about is, I almost died for many, many years because of multiple reasons, including the policeman beaten me almost to the death. I'm serious. That basically sent by the dean of the school, the Washington University. And then I survived. And I realized I need to do something for the community because I survived twice this kind of discrimination, harassment, and retaliation. So I started 3 years ago, webinar series, only featuring the young speakers, untenured professor, or postdoc, giving the 45 minutes for them. And then, but I realized nobody will watch that seminar series. So I invite big guy, including Nobel Prize winner, of course, the Francis Arnold, my academic grandma, and then now 21 National Academy member, and also the 23 funding agency directors. I never thought about how many journals we have in my field. 20 chief editor already joined as a 5-minute speaker, as a pioneer, and then 9 Nature and Cell journal editor, and then as I mentioned earlier, selected 165 rising stars. And after 3 years of weekly webinar, I realized we need to gather together. So if you are interested in going to Hawaii in December, especially East Coast people, just send the abstract. You can just type jcvi.org. You can find the abstract submission site. We try to get a lot of money for the supporting young people to travel to Hawaii. Amazingly, not that much expensive. You can buy probably $500 flight ticket, round trip, and then hotel room is less than $200. To compare, I stay one day here because MIT invite me. They pay $1,200 in Cambridge hotel, $1,200 per night. I'm talking about $200 in Hawaii in paradise, okay? This is the paper I'm talking about, my experience with the university. Type my name, science. If you are gloom or disappointed, sad all the time, read this one-page paper, you will be a little bit excited because there are many people suffering from things. And I'm chief editor of the new biotechnology. If you have some paper, anything related to biotechnology, send me email, and then I'll consider, your publication. And then I'm talking about another journal editing. I have just edited of 10 journals right now. I'm doing too much, but another thing is a process, of course. This special topic, October 34th is a deadline. So with that, I want to thank all my students and postdocs because they done all the research while I'm traveling. I'm having fun, they do all the difficult thing for me. And all the funding agency, and thank you for your attention. I'm not sure I have the time for the question, but thank you again for your attention. I'm happy to answer any question. Thank you.
Thank you for a nice talk and much more. Our next, so while we have the next speaker set up, let's have time for one question from the audience. Any questions?
Anything? Yeah.
Thank you, Professor, for the nice talk. I'm Sandeep from MIT24 India. So I just wanted to ask that the plastic that you are using, I have also worked on a project. So how it is different from a plastic pyrolysis?
So our technology at this moment, I cannot tell all the detail because I finish right now, but the basic idea is pyrolysis, basically making oil. That also we have to consider that route, but we are actually using very simple acid terephthalate and then convert that into smaller molecules, and then after that we don't need to even purify things, and that's the beauty of the system because of bacteria resistant to the whatever the treatment condition. So very simple, organic acid, very simple acid. Heat it up, and then that's the process. Pyrolysis basically you use a high heat, very high temperature, and then no oxygen, and then that's giving some oil. We might not be also utilizing that one, but that route can cost more based on our PEA, economic analysis, and then we chose to go with the other route because that can also cover to the process I listed, including PPPS and the polyethylene, PT and industry. We can extend pending more processes in the PVC and other things, but at this moment, it's for processing. Did I answer your question?
Thank you. Same to Professor Lewis. Our next speaker is Professor Kevin Wen Kim. He's going to talk about CO2 capture.
So, good morning. So I will presenting about CO2 capture, and this work is mainly done by Aphrodite Kuro and one of my associate professors, Professor Yu Yang. We do a lot of work in Ghent on CO2 capture, but this has been evolved starting from a sort of special reactor, a gas liquid vortex reactor. And we have been developing this technology for over a decade in my group. And step by step, we are moving indeed from something that has been developed in a lab to a spin-off to companies. And also my wife is very happy that I have a spin-off that makes a lot of money. So just to support that, I can only acknowledge that. So carbon capture and utilization, I think it's clear for everybody. But if you look at all the policy predictions, then one of the major efforts that people see that will be needed is CO2 capture to do something on relatively short notice. And because it's a technology which is ready, we have industrially employed plants. It requires a bit of infrastructure, but not too much. Companies see opportunities in that. Basically, they see opportunities to make money, in particular oil companies. However, there are some challenges remaining. So the energy requirement is one of them, and the cost is another point. So you see huge variety in the cost of CO2 capture. And this is depending on the technology, but also the concentration of CO2, the amines that you use, or something and so on. Of course, you have different types of technologies. You have absorption-based, you have cryogenic, membranes, and so on. But people for point sources mostly look at chemical absorption as being the dominating technology. Yeah. How does that work? Well, you start with flue gases here on the left. You have some cleanup, and then they are sent to an absorption tower. Yeah. In this absorption tower, we have an amine typically. We have a solvent in water that is basically trapping the CO2. And this means that you end up in the end with a concentrated amine, which needs to be stripped. So here the CO2 needs to be removed, and that's done via heat primarily. So the big energy consumer here is this reboiler. Yeah? And in the end, if you look at the OPEX, then all the OPEX is mostly determined by this part. So you see 70 to 80% of the OPEX is this reboiler duty. Yeah? So if you can bring this reboiler duty down, then everything else makes sense. Yeah? On the other hand, from a CapEx point of view, these absorption and desorption towers are huge. Yeah. So it's like with everything in the chemical industry, you pay for steel. The larger it is, the more steel that you need, the higher the cost. Yeah. So if we can make these things smaller, the cost will go down. Yeah. And that's in the end what we try to do in Kent. And we call that with a fancy word, process intensification, smaller and more efficient. Yeah. So there are a lot of definitions of process intensification, but I like this one of Professor Stankovic. He's one of the pioneers in process intensification. So it's a chemical engineering development that leads to a substantially smaller, cleaner, and more energy efficient technology. Yeah. In the end, doing less with more. See that you're not awake, it's more with less. Okay, good morning. Yeah. So here you see our vortex technology. This is the first generation. It looks a bit like an octopus. And it was originally developed for gas solid kind of systems. This is cold flow, just looking at the flow. Here you can actually heat things. This is for reactive purposes. We use it for biomass conversion. We use it for catalytic processes. So with the solid, you really see the solid particles rotating very quickly because you have small openings in the sides. And here comes the gas in a tangential way, and it basically drives the rotation. Yeah. And so you can see here, so you see here the gas flowing, and it's basically divided over these slits that you see here. And in this way, you get this rotational movement, and then everything leaves over the exit. So what is the main feature is that you get an intensification of heat and mass transfer. And the good thing is also you have no mechanical rotation. Yeah? This is also from a cost point of view, makes it easier, but also it makes it also more robust. And this is what we mean with process intensification. So 7 years ago, we moved, after a talk with Heinz Pitch, we said, well, actually this device is interesting, but why don't you use it for CO2 capture? Said, yeah, maybe that's a need, it's a good idea. And we did our first experiments, and we made what we call the gas liquid vortex reactor. So again, tangential inlet of the gas. So this is the red arrows. The liquid is entered in the center, is divided. And what you see is you really, so these are camera pictures, get a very large interfacial area. Yeah? So very high energy dissipation and very good momentum transfer. And this is, of course, excellent for absorption, but also for desorption. Yeah. And so over the years, we have developed this thing further. Yeah. So we see very high turbulent flow, intensification of the mass transfer. And again, we can keep this mechanical rotation, and we can avoid that. And we have optimized the design based on CFD. So we did computational fluid dynamic studies to optimize the initial structure, and we have really very small equipment. But again, the crucial step is not so much the absorption, but it's really the desorption. Yeah? And so we have here our classical desorber, and here we have the vortex desorber. Yeah? So we have here the solvent, the rich solvent which is entering. We have the steam that is needed for stripping the CO2. We have a gas lipid separator. Captured CO2 goes to the right, and here we have the lean solvent. Yeah. So again, what we want to prove is really this reduced energy requirements, because this will reduce the OpEx. Yeah. So we studied this experimentally. It's nice to study things computationally. So what we did is we have here our solvent, our rich solvent. It's fat. We have a coriolis flow meter. We 3D printed a gas liquid vortex reactor. We put it in an environment. We put detectors, 2 types of detectors to double check our results, liquid samplers, but also infrared gas analyzers. So really to be sure that we can measure the CO2 concentration at the outlet properly. And then, of course, we have our lean solvent, which is lean as well. Yeah. So here you see it in real practice. You see how small this equipment actually is. So this is really the gas liquid vortex reactor. It's very small. These are cyclones, preheaters, and so on. So everything else is a lot higher than this vortex reactor. Yeah. So very compact. And this is again, shows already the nice capex reduction potential. In this small unit, we use a gas flow rate of 15 to 25 normal cubic meter per hour, and a liquid flow rate 10 to 40 kilograms per hour. So this is a device like this, and you have this kind of high flow rates. So from that point of view, you really show the intensification potential. Yeah. We calculated energy input. Another performance index is, of course, our regeneration efficiency. So this is in effect how much CO2 comes out versus how much CO2 we actually put into the liquid. So we want to, of course, ideally have 100% of the CO2 which is in the rich amine leaving. This is, of course, not always the case. It of course depends on the design. Yeah. So here you see the results of these liquids and gas flow rates and the same geometry. So the geometry is always kept the same. And you see that we see a substantial influence of this gas and liquid flow rates. Yeah. We see that for constant gas flow rate, the regeneration efficiency increases with decreasing liquid flow rate. Yeah. Energy rate would remain the same. The liquid holdup increases, so it's obvious that this becomes better. Yeah. At best, we have a high regeneration efficiency of more than 75%. So this is a very nice, decent value. Also considering that we did not optimize the desorber design. We just used something that we had available. So this shows potential. If you look at the 3 different CO2 loadings that we studied, so these are the 3 different loadings, then of course, if you have a higher initial loading, you have a higher driving force, and of course, we have a higher release rate. So we go up in this direction. At a high liquid flow rate, so this direction, so we have that favors CO2 release rate, while a low liquid flow rate favors regeneration efficiency. So we have a bit of an optimization target that we can play with. But then we also compared our technology then to the current state of the art. So we have the classical absorbers, so these are here. And then we have the rotating packed bags, which are known to be a bit superior. But if we compare it to a CO2 release rate, then we are really almost an order of magnitude better than rotating packed bags. And so this is really a very advanced performance. And of course, then you get interest from companies and so on. So this is where we are today. A lot of interest from companies. And now we have to demonstrate this combination of this absorber and desorber on a larger scale. So at least showing that it's also possible at the higher flow rates. But it doesn't stop there. What you can also do is not so much on this absorber-desorber. You can also play with the process scheme. So a classical process scheme of an absorber-desorber has this heat exchanger in the middle, have this reboiler and so on. You can also do clever things here to reduce capex, opex, but in the end, to reduce this reboiler duty. And we did a whole study, looked at capex, opex, and PV for a classical absorber-desorber combination with MIA, because MIA is typically the solvent that is studied best. And we looked at a whole range of modifications. So the first one is this one, so intercooled absorber. Of course, it costs a bit of capex, but the solvent is partially withdrawn and generated ectothermic heat is extracted. This results in increased CO2 load, lower solvent recirculation, lower reboiler duty. So this is always our objective. This is the first thing we studied. The second thing we studied is rich solvent splitting. So we split the solvent partially, send it to the heat exchanger, but also to the top. So the cold stream is fed to the top, reduced reboiler duty. The third one that we studied is lean vapor compression. So we have a lean vapor, solvent is flashed, flash here, compressed, reduced reboiler duty. The fourth one, rich vapor compression. Rich solvent is in this case flashed, kind of flash, vapor is compressed, reduced reboiler duty. So then the last one, stripper overhead compression. So stripper overhead compression here. Desorber top is compressed, stream is partially condensed, with less condensing energy, and we don't reduce reboiler duty. So all these things are possible. They all require a bit of investment. But what you can see is that they have a substantial influence on reboiler condenser duty. So you see, this is the base case. And you see that especially this lean vapor compression can result in 21% reduction of reboiler duty. And you see that also intercooled absorbing, that basically this gives 9%. You also see that sometimes, of course, this will result in a bit of electricity. That's why you also have to look at OPEX and CAPEX. You see that in the end, for the LVC, this even results still in a lower OPEX. Nevertheless, there's a CAPEX cost for this. So you see that all these different changes in the process can really help to substantially decrease the OPEX. What is the nice thing is that they are additive. You can combine them. So, and then the result becomes even a lot better. We will publish the results soon, but that's why I cannot really share them fully. But it's really impressive what you can do with this combination. So these three combination is really has really superior performance. And this is actually what we're going to demonstrate. So we're building now a unit. Investment is around 2 million euro. So with the vortex absorber, vortex desorber, and then rich solvent splitting, rich vapor compression, and lean vapor compression. And based on our calculations, we end up with 1.7 gigajoule per ton of CO2 energy consumption. And if you compare to the best published and proven technology from BASF, that's 2.5. So we basically are 30 or 40% lower than that. So that's pretty enormous. Of course, it also depends on the solvent. So we will test plenty of solvents. Numerous companies are involved, ExxonMobil, Dow, and so on, because this can be really a major thing. And we will not go for small scale unit. We really go for a kiloton per day unit also to show scalability. And we will even demonstrate it on site at ArcelorMittal, which is one of the biggest steel producers in the world, to couple it to their chimneys. From a techno-economic point of view, you can just see from a capex point of view, and these are not our numbers. This is the Flemish Institute for Technology and Innovation. They see that there's a factor 3 difference in capex. So factor 3 reduction in capex, and also substantial reduction in OPEX. And this really shows the very nice potential of this technology. Voila. So vortex absorber desorber, I think, has enormous potential for CO2 capture. This thermal integration allows to further decrease the reborder duty. That's essential for the OPEX, but demonstration is needed to really assess the potential of this at higher tier. Well, thank you for your attention, and of course, I thank ERC and many others for sponsoring. Thank you.
Thank you for a great talk. So while the next speaker comes up, we have time for one or two questions. Any questions from the audience?
Thank you for your presentation. Is forming channels forming you are the next. Yes, you are the next.
So we have done tests with different families.
Have you copy your PowerPoint ID?
Yeah, the morning I give it to you.
Yes, I can have.
And we know it's kind of work, but